At a construction site, a pallet of bricks is to be suspended by attaching a rope to it and connecting the other ends to a couple of heavy crates on the roof of a building. So this is like the roof of a building, and then this is the pallet of brick. So I guess that they are trying to build something and they try to move the brick up or down in order to build things. So here, this is the palette of the brick, and these are the heavy crate that I mentioned. The problem statement also provides us the information about the mass of them, which measures in LPs in here, not in kilograms as usual. The rod pulls horizontally on the lower crate, and the coefficient of static friction between the lower crate and the roof is 1.666. So this is static friction. Okay, so if you remember about static friction, that's the friction occur when things still stay still. So it indicates for us that the whole system is in equilibrium and it's just like stay at rest. It's not moving yet. Okay, so it's asked for what is the weight of the heaviest pallet of bricks that can be supported this way? Start with a proper free body diagrams. And yes, whenever we do problems with forces, with motion dynamics, the causes of change in motion, we need a free body diagram. And again, what is a free body diagram? That would be a diagram free of body, which means no body shown, and we just need to focus on the forces. So in order to do that, we need to identify which body that we are working on, how many forces acting on it, and the features of each force, like which act on which, because force is an interaction between two objects, its direction, and also its magnitude, how strong it is. So let's see here, we have three objects, right? One break, the second crate, and bricks, a lot of them. And we can consider the whole thing here is like object number 3 or like body 3. They're the same thing. So in order to find the weight of this one, how much it can be supported by this weight, we can see that everything is stay at rest or like in equilibrium. So in order for this one to be supported, we really need to investigate the free body diagram for the object 3, right? So let's see how many forces acting on it. Like other problem that we discussed before, there should only be weight downward. That's the interaction between the earth and the object. Direction downward, straight downward, and magnitude, that should be just like m3g, right? That's the magnitude of the weight. The other force here should be the tension. Yes, that's the tension, because we have the string here, a rope here, and that should be upward, right? With downward, everything would just like fall down and then crash into the crowd. So that's why we need the rope to be strong enough, and it can maintain the tension to be like the same along the rope. Yes, so in order for this system to stay still, those needs to be balanced with each other. In order for this to balance with each other, then we need to know that the weight should be balanced with the tension. And here we actually don't have the information of the weight. And actually we want to determine what's the weight. How can we determine the heaviest pallet of brick, like the mass, right? So we need to find W3. So in order to find W3, we know that tension equals to it. Then we need to find the tension 3. But how can we find it? Because kind of like we don't have any other information. So seems that this approach does not really work, right? If we just like investigate the body 3 by itself, then we need to like have a look at a bigger view. So at the bigger picture, that should not be only body 3, but how about we consider the whole system here? How about it? Like 1, 2 along with the rod, and 3 is the whole system, right? And because we know that those 1, 2, and 3, they all of them will have the same acceleration, right? So that's why we can just combine them together. And in this case, we know the acceleration of 3 equals to acceleration of 1 and 2, okay? We also consider 1 and 2 together as one body as well. And they are equals to 0, right? So now, again, Newton's second law. Whenever you have these, we need Newton's second law. And Newton's second law states that the net external force will equals to the total mass times with the acceleration, and here they are equal to 0. So what is the external force that we need to list out here? We saw that for those force here, the tension, there will be like the interaction between 1, 2, and 3, right? And they just are between them, and they are inside the system. So those are just the internal forces. Because they are internal forces, that's why we don't list them here in the list here. So that's why here we just have friction. That's the static friction. It against the motion, right? Motion direction, and it has the tendency to go this way, so friction should go this way. And that will be the normal force. That will be the weight, and that could be the weight. So just more details about this one. We have that the crates 1 and 2 rest on a horizontal top like the roof here. So there should be a normal force that perpendicular to the surface like this. And then this one should balance out with the weight, right? Because the heavy crates, they don't travel, or like they don't jump up and down along this direction. They just like go this way. So then all the forces here should be balanced with each other, cancel with each other. That's why we have this one to be like 0. So what left here is just the friction and the weight. And we know that they balance each other again. So now it turns out that the weight that we're looking for, W3, equals to the friction F. Okay? And now we need to review a little bit about static friction. Static friction by definition is defined that is proportional to the normal force, its magnitude, by a coefficient. Okay, this is the coefficient, and the coefficient always like less than 1, and here is given to be like this value. So, and for this one, the normal force is also balanced with the weight. So then we can just plug in the values here of the weight. That would be the magnitude of the normal force, and then we can figure out the friction, and that friction equals the magnitude of the W3. That's why we got this result. Okay,